Hello and welcome back. Okay, so I've got one of these HD 44780 compatible modules. These are pretty cheap on eBay. I think £3 or £4 is what I paid for this one. And I want to see if I can make this talk to my processor. Now, I've got big plans for display further down the road, but I think people are getting pretty bored of flashing LEDs, so I'd like to get some human readable output from it. These things do have breadboard compatible terminals. Now, I've got this. This is the breadboard I built for the transfer register to simulate the kind of signals that I have in my processor. We don't have two buses, I can get rid of that. But what we have here is two control lines which are active low, so they spend most of their time high, and we've got 8 bits of bus data. Okay, we've got VSS and VDD. Basically power and ground. The S and D is source and drain. So this third pin, VO, I believe that's the contrast adjustment. RS, which is register select, read write. Now I'm only interested in writing to this, so I believe we can just pull that low. E is enable, so that's a signal we need to generate. And then data 0 through 7. Right, A and K are power for the backlight. Okay, for the contrast, we give it a value between 0 and 5 volts. So I should be able to use a small potentiometer for that. Feed plus 5 volts into one extreme, ground into the other, and then the tap in the middle should nicely vary. All right, let's see what that gets us. Okay, the light's on. Solid black. Okay, I would guess that the correct contrast setting is just before it starts to get dark. But we can mess around with it later if that's not panning out. Okay, so now we've got register select, enable, and the data lines. Now those data lines should be compatible with what we have on the bus. So we can just plug those straight in. So 0 on the left and 0 is on the right here. So swapping that cable over. Yellow is our enable and blue is register select. Hopefully they're long enough. Okay, so let's take a look at the data sheet and have a think about what signals this needs and what signals we're likely to get out of the CPU. Okay, I wasn't able to find an exact data sheet for this one, but this is a very similar looking module, and I believe most of the ones that look like this are based off the same chipset. It certainly lines up in the control lines. So we've got a list of commands, and okay, so this is the timing for a write operation. So we've got the read-write line, and we've already pulled that low, so that's not a problem. We have register select that decides whether or not we're writing a command or data, and we have enable. And then the data lines contain the data. Now, what's interesting here is the middle of the data coincides with the falling edge of this enable line. But this is different than the control lines we've got. Enable is active high, essentially. Now, TAS, the timing on that is 0 nanoseconds. So that's going to be handy for us. That means we can set the register select line at the same time as we're sending this line high. So actually, this is almost giving us the wrong idea of what we need to do. So we bring the enable line high at the same time as setting register select, and then when it drops back, we need to have the data on the bus, and we need to hold it there for TH, 10 nanoseconds. We need to have had the data on there for 40 nanoseconds. Okay, that's certainly not a concern for us at the current clock rates. Okay, so this is what the lines coming from our CPU are going to look like. We're going to have one line for loading data and one for loading commands, and they are active low signals. When they go low is when we're putting the data onto the bus, and when they return high is when we know the data's ready. And exactly the same for the other control line. I've just separated them out in time here. There we go. We've got a main bus and we've got these two control lines coming in. Let's have a think about what the module wants. Now I've simplified that diagram down a little bit. if we're loading data, we need the register select line to be high, and then we want to pulse the enable line. And this darker area is where we want the data to be on the bus. So this looks a bit like this. The register select line stays high, and this is basically the opposite of the load data line. But then for load command, RS needs to be low, and then this looks like the opposite of the load command line. Now, if you remember on the transfer register, we had a similar situation where we had two load lines that we wanted to merge, and we ANDed them, so then we would get the line going low for either. And that's good, but we're still the opposite of what we want, but we've used inverters before. So the big question we have is how to generate this register select line. Okay, so there's our module. Main bus, we can connect directly to it. And then let's think about this. Now, register select, I've got this line changing only here, but it only really matters during the operation. And it's actually quite a simple piece of logic we want, because if we're loading data, if this line is the one that went low last, we want it to be high. But if this line is the one that went low most recently, we want it to be low. So I'm thinking we go for a set reset latch. So for a set reset latch, we're going to use a pair of NAND gates. Now, it's more common to see these with NOR gates, but with NAND gates, it just means that the inputs are treated inverted and the outputs are inverted. So this is going to do exactly what we want. When we drop this line, it sets, and when we drop this line, it resets. So we can just take the appropriate output, stick that into the register select, and we should be generating this line. Then we want to have the two incoming control lines ANDed together and then invert the result in order to create the enable line. But of course, an AND gate with an inverter on the end is a NAND gate, and we know we've already got a NAND gate chip, so we can just use one of those. And that, I believe, is the circuit that we need. Let's build it and give it a try. Now this is a 74LS00. It has 4 NAND gates on it. Okay, so I'm going to take one of my control lines to this first input. I think what I'll do for the other one to keep things neat is I'll bring it around the back. So the output from the first NAND gate needs to be one of the inputs to the second one, and the output from that needs to be the other input to the first. Right, let's get a couple of LEDs in here. I'll turn one of these around so I don't trigger anyone. Right, let's take that first output, go there. Okay, let's give that a go. Right, failed at the first hurdle, that's not working. The wrong way around. Okay, that's cool. So whichever button we push last, equivalent LED is on. So it's high for data, so the register select line can go into the line by that LED. Right, now we need that enable line. Okay, so that needs to come as an output from one of the other NAND gates, and we need these two lines to go into it. Okay. Okay, I think that's working, but the LED is really dim. Let's go for a lower value resistor. That's better. Okay, so that actually looks like the lines we need. Plug the yellow wire in there. Okay, now A should be 65. Okay, let's go and look back at the data sheet. I believe there was something you needed to do to turn it on. Okay, there's display on and off, which is a command. So it's that bit to enable it, then this bit is on, and then this is cursor on, and that is blinking cursor on. Okay, well, that did something. There is a clear display up the top as well. So 1. That looks promising. So let's go back and put in our A. Nice. Should be able to follow the numerical sequence up. There you go. I'm not entirely incompetent at counting in binary. Okay, that's really cool. Right, I'm going to show you something else now. I got this one on eBay. Now this one came with one of those modules on the back to convert it to a serial interface, but I desoldered that and stuck a regular set of headers on. But of course I don't know whether or not it survived the process. But the ones with the module on the back were a lot cheaper than the pure parallel versions of this, so I thought it was worth a try. Okay, so what was the sequence to turn it on? That's cool. Okay, now as far as I know, we should be pretty much compliant with the signals on the bus of the CPU. So I'm going to take a brief break and bring the CPU back to my desk. Okay, I believe I've reassembled this correctly. This is the Fibonacci demo I was running in the last video. Let's see where this can go. Okay, I'm going to see if I can get a camera on this later. Let's get it in for now. And pick up the main bus down here at the ALU. I've got a nice long cable here. Okay, so device assert lines here, we've got 9 through 14, and we've got 8 through 14 for loads. Let's put that at the bottom end, so 13 and 14. Right, now we're going to need to make some changes to the ROM, and we're going to need to write some test code. Now, in terms of what's going to work in my assembler, I'm going to declare a couple of extra registers. We call that LCD command and LCD data. So we'll add an instruction out. Now we might want to come back here and do more variants, but I'm just going to do command and data from A. Okay. Now there was the initialization, and that was 14E. So we output that, and then it needed a clear, which was command 1. And then we can output characters to data. Right, there is nothing else that we should be outputting for a first test string. Hello world. Now what I've done is I've put the characters of the string in, and I put a 0 at the end. So this is going to be essentially like what we call a C style string. Just get the address of string into TX. So we load the address of SI into A. MOV will happen in pipeline stage 2, the test in pipeline stage 1. I imagine it would probably be alright if we output the 0. Then jump if not 0 to loop 1. Do we need the inc SI? pretty reasonable. We will be outputting to LCD data that 0 at the end, but you know what? I don't know what character 0 is on this, but we'll find out. Okay, so that's test code. We also need to add support for those out instructions to the control ROMs. These outs are going to look an awful lot like move operations. So we're asserting A, then we want a load from the appropriate ports. So we put data on 13 and command on 14. Can it actually be that simple? So we should start off with mov A, E. That is the correct pattern. So that should be our out. Yes, the cursor has appeared. So this should be doing, yeah, this is the clear command, which doesn't look like it's necessary. So then we're loading TL with the address of our string. So the next command is SI, TX. So this should come up into SI. Yeah, that's right. And we're loading TL with the address of our loop. So then we're going to load A with the data from SI. Yeah, that's an increment for SI. So this is a test A to see if it's 0. And this is the out. So A is not 0. So if everything we've done is correct, when this gets up to here, we should see the value in register A, which is our H, appear over there. Outstanding. Okay, now we need to see the loop complete. So that's our jump if not 0. Okay. That's our mov A, SI. Okay, let's be bold and let it go. Yes! That is amazing. Okay, that's what a 0 character looks like. Okay, I'm well happy with that. That's awesome. I was really chuffed this came down to 1 chip for the circuit. Right, I'm going to try some more test code. But I think that's enough for now. Alright, thanks for watching everyone. Goodbye.